Assalamualaikum warahmatullahi wabarakatuh. Today I would like to presenting about my research. The title of my research is about the study of conductivity and structural properties of plant-based 3D printed gel polymer electrolyte. My name is Muhammad Afiq Hazizi bin Mahmud and my supervisor is Dr. Muhammad Ifat bin Muhammad Ghazali. This is the outlines for my presentation. Nowadays, 3D printing technology has piqued the public interest in globalization due to its low cost and high precision. With the advancement of the technology, many researchers take the opportunity to investigate more deeply about the 3D printed gel polymer electrolyte, as it can fix the main problem in the lithium-ion electrolyte batteries, like leakage and low conductivity. This research focuses on the development of the 3D printed plant-based gel polymer electrolyte by 3D printing method stereolithography (SLE). For the methodology, the gel polymer electrolyte was fabricated by dissolving with different concentration of lithium perchlorate, which starts from 0% concentration until 25% concentration, with dimethyl formamide (DMF) will act as the solvent. Then the solution will be stirred with the plant-based resin and went to the photopolymerization process. To investigate the conductivity and the structural properties of the GPE will be characterized by the EIS and the FTR. Stereolithography or SLA is actually the 3D printing method with the great performance, speed, precision. This is the layer by layer photopolymerization process in which the photosensitive is polymerized with ultraviolet light. When compared to other additive manufacturing method, the conventional SLA produce better 3D printing resolution and surface quality. This is the process of SLA, which the photosensitive resin is cured layer by layer. There is two objectives in this research. First of all, it was to investigate the electrochemical properties and conductivity of 3D printed plant-based gel polymer electrolyte that was developed by the SLA method. Secondly, to study about the structural properties of the gel polymer electrolyte when doped with the lithium salts via Fourier transform infrared (FTR). For the methodology, the first one is about the fabrication of the 3D printed plant-based gel polymer electrolyte that is undergoing with the stereolithography method (SLA). In the phase 2 is about the sample characterization with the two methods which use the electrochemical impedance spectroscopy (EIS) and the Fourier transform infrared (FTR). After getting all the results, the data will be analyzed. For the synthesis of the gel polymer electrolyte and the sample analysis, first of all, the lithium perchlorate will be stirred with the DMF and the plant-based resin. The solution will be stirred homogeneously. After that, the slurry solution will be poured into the vat and the solution will be going to the photopolymerization process. And then the thin film will be obtained. For the characterization, the thin film gel polymer electrolyte will be sandwiched with the two stainless steel to determine the conductivity, and then it will be undergoing for FTR process, which to determine the functional group in the sample. The impedance plots of the 3D printed gel polymer electrolyte plant-based are shown in the figure 1, and the ionic conductivity value is presented in table 1. The augmentation of the lithium perchlorate concentration was required to enhance the quantity of free ions, which improves the ionic conductivity. For initial concentration of lithium salt 0% lithium perchlorate, the ionic conductivity reached 2.27 power of -8. The table 1 shows that the ionic conductivity of gel polymer electrolyte enhanced with the increase of lithium perchlorate concentration until it achieved the optimal level at 20%, which became 2.04 10 power of -3 with 93.37% free ion. But it began to decline above 20% concentration of lithium perchlorate due to the influence of the volume of free ions and the number of charge carriers. This occurred because of the production of ion pairs, which cause the ionic conductivity and free ions to decrease. Furthermore, ionic conductivity was found to be related to the number density of charge carriers, charge carrier mobility, and charge carrier diffusion coefficient. As shown in figure 2, the increment of ionic conductivity will also increase the number density, mobility, and diffusion coefficient of charge carrier from 4.22 10 power of 22 to 25.40 10 power of 22. The number density of charge carriers rose linearly with lithium perchlorate concentration. For the mobility of charge carriers, at 5 to 15% concentration of lithium perchlorate, the mobility increases gradually but decreases after that. The diffusion coefficient of charge carriers followed the same pattern. Ion condition cause decreases in mobility and diffusion coefficient value. Once the number density of charge carriers increased, it indicated that there were more free ions in the gel polymer electrolyte complex, which led to a major collision between the ions. Because a huge number of free ions would be moving in a small region, it will be more difficult for them to travel from one electrode to another. The free ions gradually merge to create ion pairs. As a result, the values of charge carrier mobility and charge carrier diffusion coefficient in the GPE system decrease. Ionic conductivity decreased above 20% lithium perchlorate because of this. The FTIR was utilized to investigate the functional groups that were present in the thin film sample. From figure shown, there were some peaks identified the 3D printed gel polymer pure plant-based soybean resin. In the diagnostic region, the OH stretching was found at the broad peak 3431. Besides, CH stretching was observed at peak 2926, which shows the single carbon bond of alkane in the sample, whereas a strong peak at 1721 was ascribed to the C double bond O ester group, and in the fingerprint region, the C single bond O group was seen at peak 1187. Based on the second graph, there was a minor peak at the wave number of 6 to 4 once lithium perchlorate start to dope into the 3D printed plant-based gel polymer electrolyte, indicating the ClO4 band. This may be because ClO4 is spectroscopically free. Figure shows how increasing salt influenced the ether band, which became wider because of the interaction of salt with polymer matrices as more lithium perchlorate was doped. For the FTIR deconvolution, the wave number peak at 623 and 624 represents the free ions, whereas the peak at the 632, 633 and 634 suggests the ClO4 and ion pairs in this research. From a minimum of 74.51% with 5% concentration lithium perchlorate to an optimum of 89.79% with 20% concentration of lithium perchlorate, an increasing area percentage of free ions is seen. This was due to an increase in the proportion of free ions as the lithium perchlorate level rose. This indicated that the addition of lithium perchlorate salt promotes the creation of free ions, resulting in an increase in charge carriers that would improve the ionic conductivity. The area percentage of free ions declined when lithium perchlorate level approached 20% concentration, but the area percentage of ion pairs went up from 10.21% to 12.21% at 25%. This pattern was attributable to the development of ion pairs rather than free ions being more preferred. Since more lithium perchlorate salt was added, the free ions decelerated and the gap among two free ions narrowed, causing them to unite. Thus, the elongation force among them began to associate and eventually went to neutral. Ionic conductivity can be decreased through the formation of neutral ion pairs. As a result, ion association has risen. Due to an increase in free ions and charge carriers, the stereolithography photopolymerization technique for 3D printed GPE production exhibits an optimal conductivity at 20% concentration lithium perchlorate. The augmentation of lithium perchlorate concentration was required to enhance the quantity of free ions, which improved the ionic conductivity. FTIR also confirmed the interaction of lithium salt with the polymer matrix. The combination of FTIR spectrum represents an increase in the charge carriers density with 89.79% free ions. In conclusion, SLA techniques demonstrates superior accuracy and shape flexibility for the fabrication of 3D printed GPE compared to other conventional approaches. The lithium perchlorate salt confined in 3D printed plant-based gel polymer electrolytes has desirable features and has the opportunity to be used in electrochemical devices such as batteries and rechargeable batteries in the future.